very much, and thanks to the organizers for inviting me here and inviting me to the talk. So, my talk is about finite groups, actually representation theory of finite groups. And Benjamin, in his talk just a few minutes ago, said, well, the talk is about commutative algebra, so think geometry. I was wondering if I could come up with a similar thing, and it's not going to be that good news because my talk is about finite groups, think fusion systems. So neither of those may be particularly appealing, but anyway, that's what it is. Okay, so let me start.
We all love fusion systems.
You love fusion systems as well, that is good to know. Okay, so well, let me just start out with a very fundamental, two fundamental numbers for a representation theory of finite dimensional algebras. So you take a K algebra over the field, and K is the field, and let's assume that the dimension K is finite. Then, well, there are two numbers which you can associate to the representation theory of A, or to the category mod A. Well, this is the number of isoclasses of simple A modules. Okay. So I'll call that L of A. And then you can consider the smaller number, which is the number of isoclasses of simple modules which are also projective. So clearly Z of A is less than or equal to L of A. Now the talk is really about, in some sense, or at least the background for the talk is the relationship between these two numbers. Okay. So I'm just going to give a conjecture which has actually not a direct relevance for my talk today, but I think it's very, in general for group representation theory, it is very important, somehow in the background. So this is from the 70s, and it says that if B is another algebra which is stably equivalent to A, then the difference between these two numbers, sorry, L of B minus ZB is the same. So minus ZA. Okay, so my talk is about the relationship between these two numbers, but from the prism of p-local finite group theory. So let me start with that. So from...
What do you mean by stably equivalent here?
Yeah, so that the stable module categories, the small stable module categories are equivalent. So where here the objects are finite dimensional modules and the harms are the quotients of module homomorphisms which factor through by those which factor through projectives. And I guess this is good to say because here this is triangulated.
Done.
Okay.
Those are equivalent as triangulated categories.
I don't know if he asks, if the conjecture asks for equivalence as triangulated categories, just...
You have to assume that A is Frobenius.
Yeah, sorry, I'm always thinking of self-injective.
Oh.
Yeah, sorry. When A is self-injective, then they are sometimes triangulated. Needed to get that word in. Yeah. Sorry, I knew I would make this mistake. All algebras are self-injective or symmetric. Okay. But I don't know about the triangle. So in general, it's not about the triangulated structure is not a part of this conjecture. Yes.
Yeah, but you
could ask it, and
right.
maybe when it is, and maybe I don't know whether that makes it easier.
I mean, you can even ask for like even in equivalence of stable infinity categories, which would be.
Yes, yeah, you're giving yourself even more.
I mean, but
whether you
there it would not be known.
Yeah, I don't know whether that gives how much more arsenal that gives you. I have no idea. But yes, yeah. Okay. Okay. So now let's consider finite group G, and from now on will be a field with positive characteristic, and I'm going to assume that there are no mathematical issues. Okay, is okay, and then we want to consider kg weight. So what are these? Kg weight is a pair consisting of a p-subgroup of G, and X is a simple and projective module for a subquotient of G, so a local subquotient of G. So that is, you take the normalizer in G of Q, you mod out by Q, and you now consider modules for this finite group algebra which are simple and projective. Those are called weights. And there's a natural notion of equivalence, so we consider weights up to equivalence. So we'll say Qx is the same as Q prime x if Q prime x prime can be obtained by transport of structure from Qx for some G belonging to G. And here, of course, when I say x prime is G of x, I mean up to isomorphism. Okay, so here's the background conjecture. So this is Alperin's weight conjecture. From 1987. And it says that the number of simple Kg modules up to isomorphism equals the number of Kg weights. Okay, so it's just a very, very easy statement. And okay, so let's write it out. So i.e. just L of Kg equals the sum as Q runs over p subgroups of G up to conjugation of the Z of K normalizer in G of P mod P. So on the right side you count simple projectives of local subquotients.
P equal to Q.
Q is equal to P, yes. And P is equal to Q, yes. So, yes. Okay, and this is up to conjugation.
There's a second.
Yeah, this is, P is still equal to
Just,
Q.
But they're equal, so it does not
yeah.
Okay, and I mean, if you know this is new to you, maybe as an exercise, you could try to prove this. So I call this AWC, Alperin's weight conjecture, AWC, for, let's say, I don't know, take G to be the symmetric group on 4 letters, and L equals 2, and maybe by the end of the lecture you can tell me what, so they're equal, I know this, and what these numbers are.
Is that equal to P?
P is equal, L is also. P is equal to L. Okay. So now we can refine this conjecture, and Alperin already did it, where we, instead of considering simple modules for the entire group algebra, you do it block by block. Okay. So let's look at blocks. So KG is finite dimensional algebra, so there exists a unique decomposition. You can break it up into its indecomposable factors. These are the blocks, and this is really unique on the nose. Unique decomposition into indecomposable K algebras. These are the blocks. And the module categories also break up accordingly. So in particular, the simple KG modules are disjoint union of the simple BI modules. And actually, this is not that easy. I mean, it's a bit contrived. You have to do a bit of block theory. You can also break up, naturally, the KG weights block by block. So you can take a collection of your weights, a sub-collection, and assign it to a particular block. And you also get a partition into BI weights. Okay, and this goes via the Brouwer construction. Okay, and then in the block version, let me write it over here, upstairs. In the block version, this conjecture states that the number of, well, you guessed it, I'm sure, the number of so L of BI L of BI for any weight equals the number of BI weights. Okay.
So is it clear how to talk about BI weights since it's not?
Pardon?
Is it clear how to talk about BI weights?
Yeah, so I said it's not that clear. You have
okay.
You have to do a bit of Brouwer type of representation theory. So there's this very fundamental construction called the Brouwer construction, and that's underlying almost everything in block theory, and we use that. But it's a little bit involved. So, okay, it's a good question. I mean, you can't, and that's one of the problems. At least we don't know how to do this partitioning from a representation theoretic point of view. So you can't say, oh, if you, it's just, yeah, somewhat more obscure than that. Yeah, I guess that is a problem. Okay, so, well, what do we know about this? Quite a bit now about the conjecture, but I want to actually point out one of the first papers about this conjecture, which was by Alperin and Fong in 1990. And as I'll be referring back to this later. And they showed this, showed AWC in the blockwise version for the groups, symmetry groups, and for the finite general linear groups, where in non-describing characters. Okay, yeah, I'll come back to this. And then there have been lots of cases, you know, classes of groups which were looked at, you know, through the years, and really all of them, in some sense, you feel you know enough about a group or class of groups to be able to somehow calculate on the left side and somehow calculate on the right side, and you really do them as two separate computations, and then you match. So it's really, you could be working in two different rooms. There's the global guy, there's a local guy, and you, at the end of the day, you are matched. But there is one very important...
for the symmetric group on 4 letters, they actually sort of match up in a way, right? So, like the answer is 2, right, to your question, right? So,
yes.
And the one is the trivial module, the other one is this sort of the projective modules on the symmetric group on 3 letters quotient, which is like a Steinberg module type thing.
Yes.
The question is there a preferred bijection?
Yeah. That is the question, yeah. There's no, as far as I know, there is no in general preferred bijection. In certain situations, you can, cook up bijections which look nicer than the others or which have better properties, and you sometimes need them. So, and this is what I just want to say. Mention these results because they are really sort of important in the development or in the status, state of the art of the conjecture. So these are, I think, results from 2015 or so, which say that, so they reduce AWC to stronger statement. Stronger statements. I know what I can do. I got it now. I've got the second word in as well. To equivariant versions for finite simple groups. So in other words, these theorems say if you want to prove AWC for all blocks or finite groups, it's enough to prove sufficiently equivariant bijections, equivariant with respect to automorphisms and central extensions, etc., for finite simple groups. And then you do have to do something with bijections. Yeah. But still, there's nothing really canonical about the bijections or anything like that. And so these kinds of results, if you want to prove the conjecture, they're really game changers because they totally change your idea of where you're at. Yeah, now you have the finite simple groups are classified, you work on the representation theory, and that's what's happening. Okay, but again, as the question is still coming, I guess, even if this conjecture gets proved, which we hope will be in the next decade maybe proved, it still leaves you the question of why it's true. Okay, and we'd like some more structural understanding. Okay, and so what my talk today is, I can't even say it's an attempt at that structural understanding. It's just an attempt at throwing something on the wall, okay, to try and see what we can do. And that goes by this. You have these two numbers, you expect them to be equal, you don't really know why, but maybe you can reformulate the left side as something else, the right side as something else, and then you might get closer to, seeing the connection. So, and there have been lots of attempts, especially, and this is also where will be my starting point, is on the local side. You reformulate the local side and you try to work. Okay, so that's what I'm going to talk about. And for that, I must now introduce fusion systems. Okay, so now I'm going to let S be a, for now, finite group. And a fusion system on S is a category F with objects, so it's a very small category. Objects are just the subgroups of S, and the morphisms satisfy so I write them as HOM, F from Q to R, and we want them to be subsets. So every morphism is an injective group homomorphism from Q to R. Okay, so we are really, again, we are in the realm, we stay in the realm of group theory. So injective group homomorphisms from Q to R, and we want to have a certain family which always is in there. Hom P from Hom S. Should always be contained in the set of morphisms. So this, by this, just to remind you, this I mean conjugation maps induced by elements of the big P group S, which send this subgroup Q to this subgroup R. So this Hom Q and R are both subgroups of S. And we just look at all the ways of conjugating from using an element of S, conjugating Q into R. And we also want that every morphism factors as a isomorphism followed by an inclusion. So note in particular, if Q is contained in R, is a sub, then the inclusion of Q in R is always included because you could use as your conjugation element, the identity element of S. Okay. And the way to think, I mean, what we think about when we think about fusion systems, you know, the way to think about them is what you're doing is, so the example really, is you think of S as sitting inside a group G. It could be a CLO, could be not, doesn't matter. Okay, and you let F be the category FSG. So the objects are the subgroups of S, and the morphisms, so Hom F from Q to R, is all the conjugation maps now from the really big group G. So Q to R. Okay, so that's really the categories of this form are really what we are thinking of.
So F does not have to contain all group isomorphism from condition R.
No, no.
But just enough to do the second condition.
Yeah. It just means that if you have a map from Q to R, a group homomorphism which is in F, when you restrict it to the map Q to the image of that's also in F, and its inverse is also in F. Okay, so that's all that means. Okay, well, so now just a couple of things. So I'm going to call, so I need to introduce, so if I have a fusion system like this, I'm going to introduce a group called the outer automorphism group of Q in F, which is just all the F automorphisms of Q, and you mod out all the inner automorphisms of Q. So if you think about this example, you're saying you take you're really looking at NG of Q, okay, mod CG of Q, yeah, so all the group conjugations, self-conjugations of Q, and you're modding out by Q. So in this example, if I look over here, yeah, in the example, this is just the group NG of Q mod Q CG of Q. Okay. So anyway, so this is a finite group. So you can form its group algebra, and then you can start counting its modules. Okay, and that's what we are going to do. So Okay, and so then we are going to count. So now we're going to define a number associated to this fusion system. And I'm going to explain this. Eccentric radical. So you take all subgroups of S, which are F-centric radical, I'll explain what that is, up to conjugation, that is up to F isomorphism. Okay. So take one for each isomorphism class of these types of subgroups of S, and you count the number of simple projective modules of this group. Okay. Okay, so you can do that, it's a number. Here, and what is F-centric and radical? So Q less than Q inside S is F-centric. This is really a translation of the property of being self-centralizing. If for all Q prime, which are isomorphic in F to Q, we have that the centralizer in S of Q prime is contained in Q prime. And it is a radical if this outer automorphism group, out F of Q, has no non-trivial normal p-subgroups. Okay, it's a general fact. Basic fact that if you want a group algebra to have a weight, you know, to have a simple projective module, it better not have any non-trivial normal subgroups. So when you're counting simple projectives, you have to be in this radical situation. Okay? Yeah.
So you could have omitted the word radical and it wouldn't make any difference.
It wouldn't make any difference. You can omit the word radical here. I'm keeping it because in the end, if I get to it, I need to do radical as well. So. But you're right, here I could just do F-centrics.
And the twiddle is F isomorphism?
F isomorphism, yeah. Okay, so you have this simple-minded, you know, thing. Okay, and now, so what's the connection with the
what would be those things when F is in your example of this key?
Something. Yeah.
So in the symmetric group sigma 4, for instance, it would be the Klein 4 group and the CELO subgroup. Right?
Yeah. If the fusion system was the fusion system on the CELO of S4.
Yeah.
Okay, so I think now I need to do the most dreaded thing of all, which is erasing.
It's a fun part. Dave has actually offered to take over as Dinger. This is a professional, you know. So.
Actually, maybe I can. No, I think I need to. Let me just keep that side. I know this is conventional. You only erase half, right? But I'm going to do that because I want to write on that side. Okay. Okay. So again, that's good because now there's quite a few things on the board. So what is a fact? Again, coming from block theory, totally not, you know, easy, sort of elementary to describe. So I won't describe it. But here's a fact. Linking these stuff on the board together. If B is a block of some finite group, okay, then from the local block theory, To B is associated a finite P group, which is a subgroup of the ambient group, of which this is a block, a finite P group S, and a saturated fusion, and a fusion system. F on S. Okay, you can do this. This is coming from theory of defect groups and Brouwer pairs, etc. Again, you use the Brouwer construction. Such that, what happens? That the number of B weights equals this purely local number, the number of weights of F. Now, already I am lying here. I'm making a very important but aesthetic choice. This is not quite true on the nose, okay? There's another little piece of cohomological information that you have to throw in general, okay? Where instead of considering here NGQ mod Q, you have to, and the group algebra, you have to consider twisted group algebras coming from two cohomology classes. I don't want to say that because it won't add anything to the talk. So let me make this statement correct on the notes by saying this is true for certain types of blocks called principal blocks. Okay, so so if we add here a certain type of block, principal block, that is the block which contains the trivial G module, then this is correct on the nose. Okay, and otherwise you have to deform this a little bit. Yeah.
What are the quantifiers on this statement? Like for all F or for all?
No, so for all blocks, for any block B, there is a canonically associated fusion system.
Oh, which you fix, okay.
Yeah. So B determines. Sorry, maybe I should say a fusion system F, which is F of B. There's no choice. B is giving you a fusion system.
When you say it's canonical, you mean I'm given a block of a group. I'm not giving it as an algebra.
No, yeah, as a group, always embedded in a group, yeah. The group is there behind in order to just. But the point here is that you can have many blocks sitting in totally different groups, which all have the same fusion system. Okay, and they all will have then the same number of simple modules.
But the algebra doesn't remember the fusion system.
No, that's a big question. The algebra doesn't even remember, it doesn't even know S. The algebra doesn't even know, algebra really knows nothing. Algebra doesn't even know as, well, I guess maybe now he doesn't know, whether S is abelian or not. Algebra knows nothing. Yeah?
In the non-principal block case, the left-hand side stays the same, but you have to change the.
You have to change, So what you have to change here is, I can write it down.
You have to change W, or you have to.
You have to change W, yeah.
So I'm just confused that you were correcting this, which looks like the left-hand side. You're trying to edit the definition of W or of L?
Of W.
Of W, yes.
Yeah.
And in which case you would have to change the group algebra of this outer.
You keep that. Sorry, where am I here? Sorry, I started editing on the wrong board.
That's what I'm saying.
Sorry, I'm so sorry. I'm so sorry. It should have been on that board. The out F of Q stays the same. But you don't look at K out of Q, but you look at a twisted group algebra. So you don't look at a honest group algebra, but you look at a twisted version.
But you still recover what you care about.
Yeah, so you kind of have to put, for all these QF-centrics, there's this theory of Kuhlsheimer-Puch classes, which are two cohomology groups. I have to put that in. Okay, and it's quite complicated, but I don't. And there are questions around that, about what alpha Qs arise and all. But I'll just stick to this. For this talk, we can just ignore. Okay, so anyway, AWC becomes the statement that for any block with the number of simple modules equals the number of weights of F. Okay, and now the point is, so you want to kind of understand this equation, like I said, in any which way you can. And the point of view of this talk is, well, this quantity makes sense in a very general situation. You know, when we wrote WF, we just started with this small category and we messed around a little bit and we got this number. And so the question is, well, very big question. And but I mean, it's a question with some meaning, because they exist fusion systems which are not fusion systems of any block. Okay, so there are exotic fusion systems. So the question is, does WF count something even when F is not the fusion system of the block? Or, I mean, even if it is, can we sort of understand WF, free it from the block, and understand it better? Okay, so, well, you could say, well, it counts itself, so what do I mean? So I'm just going to try and give you now it's really just a smattering of results, okay, to show that, okay, you can get interesting answers to this question even if you don't exactly know what the question is, okay? So I'm just going to do a few of those things. Okay, so what should I erase? How much time? I don't have much time, actually. 10 minutes? No.
A bit more.
Bit more? 15? Okay, well, I better hurry up. I think.
You know, it's 15 minutes plus questions, but if there are many questions during the talk, then
Okay.
you can use 10 minutes. Oh, this is not offending the crowd.
Well, I'm really much slower than I thought I would be.
Because we ask questions.
Yeah, well, so anyway. Okay.
And because Dave didn't sing. Nu er det jul igen, og nu er det jul igen. Danish Christmas song.
An excerpt of it. It's a full song.
Okay. So okay, let me just first give a result which maybe justifies to some extent why I want to count, okay? Alternating sums. I just give one result in this direction. So as I said, okay, WF is certainly a non-negative quantity. So it's counting something, but in the next result maybe it's not so obvious. Okay, so I'm going to give you a reformulation of a cancellation theorem of Jeff Robinson. From 1991. Okay, and this has also a provenance. I mean, soon after Alperin came up with his conjecture, there was, well, thanks very far also to work of Peter Webb, there was a realization by Kinner and Robinson that you could have you could express this equality in terms of some alternating sums over chains. Okay? And this is going back to that. So I'm just going to write it. B is a block, assume principal block. So B is a block with fusion system F on P group S. And now you can count something else. Okay, so you could count the dimension over K. Well, this is a finite dimensional algebra. It has a center. So let me write it as the center. That's a subalgebra. You can count its dimension. Okay. And the cancellation theorem of Robinson says that you can do this by counting over some chains in the fusion system. Okay. So I'm just going to write Q sigma X, and the point here is that sigma are some chains. And then you count again some projective simple modules of some groups, okay, which are subgroups of these out F of Q's, but now you have to look at stabilizers of these pairs sigma and X. The exact form is not important. I just write down what sigma runs over chains up to some isomorphism of p subgroups. I should say some chains, normal chains of p subgroups. In out F of Q, and X runs over conjugacy classes. Of elements of Q. And this out F of Q sigma X is the stabilizer in out F of Q. Out F of Q acts by conjugation on everything. All the action is happening in out F of Q. Stabilize an out F of Q of the pair sigma and X. And you count up to suitable notions of isomorphism. Okay, as I said, it's not important for this talk exactly what how these chains come up. And there are many variations, okay, and many refinements, okay, where you count different things. So this is the Alperin's weight conjecture is part of a big sort of edifice of counting conjectures, and lots of them are expressible in forms of these alternating chain values. Okay. Anyway, so this is quite miraculous. It says that if you do this and you do all the yoga here, in the end everything will cancel, and what you'll be left with is the number which is the dimension of the center of B. But if you look at it from the on the right hand side, okay, well, it's not obvious at all that you're going to get a non-negative. Yeah.
I'm feeling a little confused with all the notation.
Yes.
Shouldn't it be over chains of Q, not over subgroups of
No, it's chains in out F of Q.
Okay.
Yeah. Because, yeah, exactly. So, I mean, you have to do a bit of work to see that that's what he's saying. But it's over out F of Q.
It's proper.
And they start at 1. They are proper chains, sorry, and they start at 1. That's important.
It's an infinite series.
Yeah. Proper chains, and every one of them is normal in the top guy.
If it were like the principal block of a group or something,
Yeah, it is.
and you've got the whole Zeeloff P subgroup as the defect group, you'd be summing over chains of that P subgroup, would you not? Or not of.
You see, okay, hang on. Yes, you're right. So, you're right. Because out F of Q is ng of q mod qcg of q, its Celof subgroup is going to be n sub s of q, for suitable if q is chosen fully normalized. So eventually, then you are summing, you are doing chains in subquotients of the Celof subgroup. So you're right. Yeah, because of the various properties, if q is chosen in its conjugacy class to be fully normalized, then the out S of q is a Celo of this group. And so all chains can be conjugated into a chain of subgroups in that group. So yes, you're right. Yeah.
So you've got an alternating sum over p subgroup.
Yeah.
Right? Could you just do it over elementary abelian ones?
There's all kinds of reformulations. There's elementary abelian, there's radical, there's all kinds of and I mean there's a lot of work, and Peter is in the audience, and he knows the most, I think, about that.
Any collection of p subgroups where the complex is equivariantly homotopy equivalent to. That's what we think of, and they are equivariantly homotopy equivalent.
Is this a homotopy invariant statement?
So I don't know about this particular formulation, because this one is, I don't know whether the homotopy theoretic, whether things are true for this particular sort of expression. Okay, but yes, definitely, and that's the background interest of these things.
Be a little bit careful here because it's just a block, right? So you can't just do a homotopy on the whole thing. So.
Yeah. I mean, so that. Yes. What was I going to say? Right. So anyway, so here's this sum over chains, alternating sum, and it's not clear that this counts anything at all in general. But here's a theorem. So this was going to work with Marcus Linkelmann, Lind, and Justin Lind and Jason Semeraro. It's from quite 4 or 5 years ago now, and it says, suppose f is saturated, and this I have not explained, but actually all the things that I'm interested in is for these special types of fusion systems. All blocks fusion systems are saturated, and so it's really not, I mean, our world really is about saturated fusion systems. I just don't want to give the axioms for saturation, so avoiding that. So suppose F is a saturated fusion system, doesn't matter what, which one, nothing to do with blocks, then we can cancel chains. So here, if I call this guy MF, I'm just going to call this, give it a name, the right side. Okay, so so that may be some indication that there's something going on.
Is it the dimension of the center of something?
Don't know. That's the question. All we know is that it's positive, right? And you can give a formula. That's it. Don't know. Don't know if it's the dimension of anything. But it's just an indication that it is counting something. Okay, so that's one theorem, and then I will give another theorem which is totally looks different, okay? But, yeah.
I want to push the bottom up before you.
Okay. And I mean, this theorem in this paper that we wrote, this theorem is sort of the starting point. Then we can do refinements or talk about conjectural refinements and make links make analogues of counting conjectures in block theory in the realm of fusion systems. Yeah, we've checked them for small fusion systems, exotic ones, and they check out. But I don't want to. Good. And then I will give another theorem, which is more Lie theoretical in nature.
What is this number for the Solomon exotic fusion?
Oh, this one we can't calculate. This number is too difficult to calculate. I think Jason and Justin did some attempts. They calculated the weight. They calculated WF, and it's always 12. Yeah, no matter what Q. So you know they. Yeah. So this is, I should say, it was really. Justin Lind and Jason Semeraro who kind of started us off on this. And they started us off by calculating the weights of the Solomon fusion system. And I think the answer is 12 for any Solomon fusion system. And well, the next one I'm going to write down now is going to maybe give some justification for that. Explanation for that. Okay, so if you permit me to go a little over 15 minutes, maybe I can get to it. Okay, so let me just actually go back to the example of Alperin form, GLNQ, finite general linear group, and I'm going to make life even easier for myself. P divides Q minus 1. And, well, so GLNQ has a maximal torus, which is the group of diagonal matrices, and has a Weil group, which is a symmetric group. Okay. And if you look at the paper of Alperin and Fong, from the prism of fusion systems, what they actually calculate when they show that the weight conjecture holds is they show. So this is 1990. They show that if B is the principal block of G in this case, and F fusion system. It's a really beautiful equality. They show that the weights of F, the number of weights, equals the number of ordinary irreducible complex valued characters of the Weil group. Okay. And then there's a lot of representation theory, a la Lustig. So this was the second part of that, Lustig style representation theory of finite groups of Lie type tells you that this actually also equals L of B. And so you get Alperin's weight conjecture. Okay. For that case. Okay. So W is the Weil group of this finite group of Lie type. So this kind of principle sort of carries over to other finite groups of Lie type as well. And more generally, it carries over to the more exotic situations. So where now, instead of looking at Weil groups, you look at L-adic reflection groups. And well, we are meant to think of these as the Weil groups of p-adic reflection groups, and we are meant to think of them as the Weil groups of p-compact groups. You know that by now, or at least I know it since 2 years ago. But anyway, p-adic reflection groups, and finite groups of Lie type are homotopy, fixed points under Frobenius morphism. So here you take fixed points, homotopy fixed points of unstable Adams operations. And then you do some local homotopy theory or p-local group theory, and you get out. So here is work of Brotto-Müller from 2007. They show 2W via this theory of p-compact groups, 2W and a prime power Q with P not dividing Q, and they also assume that P is odd. To this data, you can associate a fusion system. Okay. Fusion system F on some finite P group S, which, if you were in the if your p-compact group was the p-completion of a real compact group, a proper compact group, would give you fusion systems of these finite groups of Lie type. Okay. Anyway, so, and you get these, so and you get some exotic ones as well. So I'll call this F. So this depends on W and Q. And the theorem,
It may be worthwhile like to mention that Dave actually first observed this kind of thing for P equals to 2, which was some of the...
Yes, for the Benson-Solomon fusion system. Yes, absolutely. This is going back, to Dave and to the classification of finite simple groups and all that. That you can do this for non-violent groups. Yes, you're absolutely right. Yes. Okay. Anyway, so what's the observational theorem? And I'll stop here. Which is joint work now with Gunther Malle and Jason Semeraro, is that under these hypotheses, and assume we need some goodness assumption, so that's something a little bit more than good in the sense of Lie theory. So I'm just going to call it P is very good for W. Then these fusion systems, if you do the weight calculation, you get. I have to add some more things. The number of irreducible characters of the Weil group. I'm giving only the case that P divides Q minus 1. For you, that's not, the theorem works for every case. You just have to replace then the Weil group by a relative Weil group, depending on the order of. Okay, so So again, this is also only the start of the story. We really want to do some kind of representation theory. We want to have some. So in the setting of complex reflection groups, there is this attempt by Bouet, Malle, and Michel, going back to the 90s, where they try to develop a sort of character theory for mythical objects, which would be like finite groups of Lie type if this was a Weil group. Okay, and you can do that because Lustig has told us that actually the representation theory of finite groups of Lie type is somehow combinatorial, and it really depends on the Weil group. So you can take that and you can start generating data from a complex reflection group, and you can get like a kind of character theory. Okay, and so we've combined, the p-compact group theory gives us a local structure for this mythical object. Yeah, it gives us CELO subgroups and a fusion system, and so we can combine this to do some character theory for a principal block of this mythical thing called a Spetz. And all we have to report is that the data is kind of consistent. Yeah, some numerical things you would expect do work out. It's very complicated to establish it. so I don't say more about that. I think this is a good place to stop.